Yeah. So first of all, if you look at the discussion part, okay, I'm going to use this discussion part to bring in the theorem that I want to teach today, okay? So if you have a look at the discussion part, okay, X is the score for the spins. So this is the population. So now my population, I build the probability distribution table for it. So I have the 4X value that is 1, 2, 3, and 4. So that means in my population here, I only have 4 numbers. Okay, I only have 4 numbers, correct? In the real life, you can't have a population with only 4. Population like population of teenagers in Malaysia, there are thousands of them. Okay, so the probability of getting each one is 1/4. All right, according to the spin, the section. Am I right? Hello? So can you please help me to find the population mean? Can you please help me to find the population mean? Hurry up. And the population standard deviation. I mean, the standard deviation of the population, we call it X. The variable that we have here is X. You can't join. 834 1206 9741 832 948. Huh? The password is incorrect. Eight 34 206 9. Incorrect password. Eight 32948. Okay, so what is the mean? The mean is 2.5, correct? Hello? Okay, what is the standard deviation? 1.21, right? 12. 1.12. Okay, good. So this is our population. Now from this population, I'm going to draw a samples. Okay, then my variable of interest is the sample mean, is not the value of each sample. Are you clear? So from the first spin, I got how many possible outcomes? I have 4. Am I right? 4. And we always multiply, correct? You talk about everyone have an equal chance to be selected. That means when you spin again, you may get the same number. Am I right? So there are also 4 possible outcomes. So that means from here, my exotic sample. So how many possible samples can be obtained? I can have 16 possible samples. You can imagine your population only got 4. When you choose a sample of sample size 2, you can have 16 possible samples. So if my population got 10 members, for example, 10 value. So if I want to select samples of size 2, so how many possible samples can I have? 10 times 10, 100 possible samples. These are called exotic samples. Exotic sample, that means all the possible samples. Are you clear? So listen here carefully. In real life, your sample is your population is very huge. So it's impossible for you to get exotic samples. If you want to get exotic samples, I mean, all the possible samples is going to take you a long time, maybe 10 years, 20 years. By the time everything is outdated. Are you clear? So we are going to use this, a small population, to bring you to the concept of central limit theorem. Are you clear? So whatever happened here, it doesn't happen in real life. Do you get me? Okay, so now in this part, am I interested in X or am I interested in what is my variable that I'm going to talk about? Look, my variable is the sample mean, which means that, listen, which means I'm going to build a table first. In real life, you can't build, okay? Okay, so I have many samples, first spin, second spin. And for each sample, I'm going to find the mean. So this is the variable that I'm interested in. I want to see how is the distribution of sample mean. So I want to study how is the distribution of sample means. So my variable of interest now is the sample mean. Are you clear? So each sample, I will find the sample mean. So altogether, I got how many samples? 16 samples. So can you please list down all the 16 samples? And each sample, you find the mean, please. 1, 1. The mean is 1. 1, 2. The mean is 1.5. You know how to count the mean, correct? Go on until all the 16 is covered. 1, 3, 1, 4. Continue by yourself. 2, 1. 2, 2, 2, 3. Faster, do by yourself. 2, 4. And count the mean. 2, no more 2. Go to the next one. 3, 1, 3, 2, 3, 3. Okay, please. How about 1.5? 1.5 appear here 1 time, 2 times, correct? So the probability of x bar 2 to be 1.5 will be 2 out of 16. The next higher sample mean will be, Christopher, the next higher sample mean will be 2. Okay, 2 appear how many times? 1, 2, 3 times. Am I right? Hello? Are you with me? Okay, 3 times. Okay, what is the next higher sample mean? I'm talking about here, this column sample mean already. Here, this column. The next sample mean will be 2.5. 2.5 appear how many times? 2.5 appear 3 times, 4 times. Correct? Okay. Then after that is 3. 3 appear how many times? 3 times. Then 3.5 appear 2 times. Then 4 appear 1. Done. So can you find? So look at, look, here is my population of sample mean. So if I write like this, population, correct? If I write like this, so how I read? The mean of the sample mean. So that means my variable is x bar 2 here. Are you clear? That is how you read. And this one, how you read? This is the mean of the population X. And if I want to read this, I also can say the mean of the population of sample mean. Get me? So can you please use your calculator, key this into your calculator and tell me what is the answer. So every time when you write this symbol, that means it belongs to the population. And the subscript here is the variable that you are talking about. I can tell you the answer because I know the formula, 2.5. Right? So if I write like that, that means I'm talking about the standard deviation of the population. Now I add in the word population of sample mean. So this one, my variable is X bar 2. So that's why I can use this symbol. So answer 0. 0.791 or 792. Huh? 0.791. Is it? You key in. Yep. Hello. Okay, huh? So you have to know which population are you talking about. You are talking about the original population, or you are talking about population of the sample mean. So your variable of interest in this case is the mean of each sample. So you take the exotic sample. So this is the population of your sample mean here. Are you clear? So now I'm going to put these two side by side, and I'm going to talk about whatever we have in page 264. Okay, so everyone, you can turn to page 264. Okay, so now this is my, okay, I'm going to use the example and explain everything there. Original population. There's our X. Okay. Sample mean population. But in actual fact, you don't say sample mean population. I just add in the word to let you have the sense of population. We just say sample mean. So this is our sample mean that we are talking about. Yep. From our example, the mean of X is 2.5. The sample mean, the mean of the sample mean is also 2.5. All right. The standard deviation of the sample of the original population is 1.12. The standard deviation of the sample mean is 0.179. 197. 79, I'm right. So look, 791. 0.791. Okay, now, why this one have a smaller spread? Why this one have a smaller spread? Who can explain to me? The reason is because sample is part of the population. Sample is a representation of the population, correct? So the mean of each sample should be quite close to each other, correct? So that's why the spread is smaller. Get me? That is the first thing. Samples, especially if you take the random sample, it is part of the population. Correct? So the mean of each sample should be very close to each other. And the mean of their mean should be the same as the population mean. Am I right? So that is the first thing. So that is the first part of the central limit theorem. That is, the mean of the sample mean is equal to the population mean. So I have two different distributions. One is the distribution of the sample mean. One is the original population. Okay. then the standard deviation of the sample mean distribution will be equal to the standard deviation of the population divided by square root of n. The larger the sample size, the better the sample represent the population, correct? So the mean of each sample, the variation should be smaller. That's why you divide by square root of n. So that is the first part of the central limit theorem. So, and this is the part that every one of us have to remember. Okay. Second part is talk about the shape of the graph. The shape. So if you take just now our original, we plot the graph. We only can plot a spike diagram, okay? If it's 1, 2, 3, 4. All the probability is 1/4, correct? So it's a uniform distribution, am I right? But if we plot, can you please now plot the distribution of x bar n that we have just now? Start with 1, 1.5, 2, 2.5, 3, 3.5, and the last one is 4. Hello, please plot. Take your paper and plot, please. So if you look at the shape of the graph, we call it symmetrical, correct? It's symmetrical, correct? So that will bring you, if you read the central limit theorem in your textbook, page 264. The population is not symmetrical, correct? But the sample mean is symmetrical, am I right? Hello? So let me bring you to page 264 of your textbook. I'm going to read you. Suppose x is a random variable which is not necessarily normally distributed. This is not normally distributed. Okay, you better listen to this carefully, because you are going to present this in your folio. Your folio without this, I sure fail you. I'm telling you, you didn't explain your central limit theorem properly, I fail you straight away your folio. I give you an E. Suppose x is a random variable which is not necessarily normally distributed. X has a mean of this one and the standard deviation of this. For sufficiently large n. So if my population only got 4 members, my n is equal to 2. Do you think it's sufficiently large? No, meh? Out of 4, I pick 2 not large. I take half of the population, not large. Large. It's sufficiently large. The distribution of the sample mean of size n is approximately normal with the mean of this and the standard deviation of this. And we have proven it. This is approximately 1.12 divided by square root of 2. Am I right? Am I right? Okay. The larger the value of n, the better the approximation will be. So you see, it is not easy to understand this statement. The larger the value of n, the better the approximation will be. Which approximation am I talking about? Please answer me. You don't answer me, I will not continue. Which approximation am I talking about? Why is it that the larger the value of n, the better the approximation will be? So if they tell you that the better the approximation will be, what does that mean? Okay. Huh? More compact. If you tell me more compact, statistically, I won't think that you are right. There's no such thing as I'm packing something. Yan, I'm not packing something. So you cannot say more compact. Mustafa, you better speak out because you're going to write. If you don't speak out, you are going to write rubbish for me. And I give you rubbish mark, I'm telling you. Yes? Narrower? What do you mean by narrower? You see, when you use statistic, when you talk about statistic in this case, the two important things. If you say more compact, what term should you use instead of saying more compact? If you say narrower, what term must you use? What is the term? What is the term? You please don't say narrower or that one. You don't use more compact. You have to use statistical word. The question said the larger the value of n, the better the approximation will be, means the standard deviation of the sample mean will be smaller. Because of this formula, you see, it's understood. The bigger the sample size, the better it represents the population, correct? So the mean from each sample should be closer to each other, which means that we will obtain a smaller standard deviation. And statisticians have found out that the relationship is divided by square root of the sample size. That's why you divide by square root of the sample size. So the statement, the larger the value of n, the better the approximation will be. It means that if I choose a larger sample size, that sample will give a better representation of the population. So which means that the mean of each sample will be closer to each other. Am I right? So which means that the distribution of the sample mean will have a smaller standard deviation. Clear? Okay. Look. So now I'm going to talk about the shape of the graph for central limit theorem, different from how your book phrase it. Okay, different from how your book phrase it. So when you talk about, if you look at the second point, if you look at the point, we note that many texts suggest a rule of thumb of n greater than 10 to indicate n is large enough. However, this value depends on the nominality of the original variable x. Okay, so now I'm going to break this statement into two statements. So when you talk about statement, usually in maths or in English, cause and effect. If something, something, then something, something. Am I right? Because the question said normality of the original variable. Okay, so now I'm going to this first part. If the population X is normally distributed, for whatever sample size, or you can say regardless any sample size. Okay, sample mean distribution will be normally distributed. Do you get what I mean for this statement? If the population X is normally distributed, regardless of the sample size, the sample mean sure is normally distributed. So I don't have to follow the thumb of rule of n greater than 30. Are you clear? Okay, so now I want to test your understanding. Look here, I want to test your understanding. So look. So this is my distribution A. This is my distribution B. Okay. Which is X? Which is X bar 10? Why? Okay, answer. Answer. Yes? Okay, A is X. And B is X bar 10. Why? Because all right? Because we know that standard deviation of x bar n is equal to standard deviation of the population divided by square root of n. I forgot to write down. You also don't write down. Yes? Why? How to? Because what is the reason you choose like that? Because the spread of B is bigger or smaller? Smaller. Both are normally distributed. Correct? I say if the population is X is normally distributed for whatever sample size n. Sample means Xn distribution will be normally distributed with a smaller spread. Am I right? So that is the reason you give. Just how we quote that example, correct? The spread is smaller, correct? Compare. Yeah. Okay, now I want to test you again. If I got okay, which is X bar 20 and which is X bar 40. Why? Okay, any of the girls? Hurry up, tell me, select. Yes. B is X bar 40. Okay. So why? Because 40 is greater than 20 and the distribution, the spread of B is what? Smaller than A. The bigger the sample size, the better the samples represent the population. So the sample mean distribution will have a smaller spread. Are you clear? So that is talking about the shape, huh? The first part. Second part, talking about the shape. So central limit theorems, you have two parts. One is talking about the relationship between the mean and the standard deviation. The second part is talking about the shape. And the shape will depend on the population shape first. Are you okay? Okay, now. So the second part, if the population X is not normally distributed. The sample mean distribution will become normally distributed as the sample size increases. So that is what you talk about. It approximately normal with the mean of this and that kind of things. Okay. As what we have done just now, our population only got 4 members, correct? That's, yeah. So we take a sample of half of the population. So by thumb of rule, in the real life situation, the n must be greater than 30. Then your sample size is considered large enough. So for this case, when will the sample size be large enough? When n is greater than or equal to 30. This is thumbs of rule. So the first point, the first bullet in your page 264 only apply in this case. It doesn't apply for this case. So if I know that the population is normally distributed for whatever sample size, doesn't matter. The sample size is large enough to make it normal. But if the population is not normally distributed, okay, then by thumbs of rule, in order to justify whether your sample size is large enough or not, you take n greater than 30. Okay, but look, so now I'm going to test you again on the understanding of this. I don't have to tell you the spread, okay? Okay, which is X and which is X bar 5. Why? Or I can put explain. Okay, this question, any of the boys? Hello, you keep your mouth shut, exam also shut, hurry up. X bar 5 is which one? Okay, X bar 5, A is the distribution of X bar 5. Why? Why? Because Sebastian, answer, reason. So why don't you say because A is normally distributed? Yeah, because A, try to make a positive statement instead of negative statement. Because A is normally distributed. You see or not? The way you answer this question will be different. Depend on what I give you. Okay, now I give you another one. Okay, so can I? So I give you another one. I say given, this is my X bar 10. Then I ask you question. Is n equal to 20? Okay. Is n equal to 20? Is the sample size of 20 large enough? Explain. Girls, is the sample size of 20 large enough? Explain. There's no girls in the class other than me, is it? So I have to explain, is it? Hurry up. Is n equal to 20 or sample size 20 large enough? No. Why? Less than 30. Do you see I give you the graph of X bar 10? Is the sample size of 20 large enough? The answer is yes. Because 20 is greater than 10. And the distribution of X bar 10 is normally distributed. You see or not? When we use the thumb of rule, that means we have no other information. Do you get me? Now I got give you the information. I've given you the distribution of the sample mean of size 10. It's normally distributed already. If the size 10 will give you a sample mean distribution normally distributed, 20 will give you a better representation. So it should be normally distributed. Because based on just now the statement we say about if the population is not normally distributed, correct? If the population X is not normally distributed, the sample mean distribution will become normally distributed as the sample size increases. If with the sample size of 10, it is normally distributed already, how you increase the sample size, it will be normally distributed. Am I right? Are you clear? So you have to depend on how the question is asked. Do you get me? So if we talk about the sample is a normally distributed, so that means whatever probability we want to find, we can use the normal CDF, correct? So that will be your exercise 9C and 9B and 9C all about. So I will discuss, you can try to do all the question there, then I will discuss one by one with you tomorrow. So what is important is, this central limit theorem allows us to justify what is the range of sample mean that I may have. Then from there, we will learn how to predict the population mean. Listen here carefully. In real life, you don't know your population mean. But in all the questions here, they give you the population mean. In real life, we are doing the reverse. We use a sample mean to make a prediction on the population mean. But in all the questions here, they give you the population mean. and talk about the sample mean. Are you clear? So you don't take the textbook question as a real life scenario, okay? So that when you write your folio, you won't get confused. Are you clear? Okay? So first, why must we have this theorem? So that we can make prediction later on. Because if it's normally distributed, if you study higher up, they don't use normal distribution. They can use chi distribution. They can use two-tail distribution, a lot of others. Skew right, skew left, and so on and so forth. So those who want to study actuarial science, that is where you will talk about a lot. We only study about two distributions. In statistics, there are more than two distributions. Okay? Yep. So depend on the nature of the population, you make the prediction. Okay, thank you, class.